Hi, everybody. Very, very exciting. We are about to jump in to 2.7. Finally, our derivatives introduction. We've done enough groundwork, laying the groundwork with limits. We can finally talk about the huge, huge concept in our course, the derivative. Obviously, we're going to be building on this in other sections, but finally, here we go. Okay, what's this all about? We want to know the instantaneous rate of change of a function at a given x value or at a given point. The instantaneous rate of change of f of x at a. We'd really like to know how fast things are changing, and even down to the how fast is something changing at any given instant in time. Graphically, right, if we had a function to describe how something was moving, let's say, like that orange function you see here, then what would it mean graphically to represent the instantaneous rate of change at any given moment? So we would find our moment, or our x value, a, right? Where is the point there? And we would draw this line. This line is going to just barely graze by the function at that point. Here, it only passes through, it only touches f of x just at that one point, and it kind of just grazes by, barely touches it right there, and then keeps moving on. The idea is that this green line right at that moment is moving in the same direction as f of x, even though f of x continues to curve away. Right at that moment, the orange line is almost like pointed in this direction. We give that green line a particular name. We call it a tangent line. We use the word tangent, kind of in everyday language. I'm going to go off on a tangent really quick. We're kind of like going kind of in a different path from like the mainstream of the conversation, but there's a connection, right? So it's kind of the idea. Now, what is it about the tangent line that represents the instantaneous rate of change? And it turns out it's the slope of the tangent line that we're after. The slope tells us a rate. Think like a rate, something like miles per hour, or dollars per year, or something like that. How fast is this moving? Right? How fast is the y value moving with respect to the x value? So there's two units involved, like miles per hour, right? How fast is it moving? Okay, interesting. How we got to figure out what the slope of a tangent line is? I mean, it only passes through a single point. I can find the slope of a line if it passes through 2 points, but not if it just passes through 1 point, or 1 point that I know, right? So what are we going to do here? Okay, we're going to use some pre-calculus or even like algebra concepts, very simple algebra concepts, but we're going to notice a certain pattern, and it's going to allow us to connect that idea with limits. Okay, check this out. Consider the average rate of change from another point, let's call it x. So we'll say we got our point x over here, or our x value x, it's got its point, and our same point at a. What would be the average rate of change? So it turns out the average rate of change is if we were to find the slope between those 2 points. We can draw that line, and if we wanted a name for that line, it turns out it's called a secant line. Now, when we use the words tangent and secant here, there's no connection to the same language that we use in trig. The tangent function and the secant function just happens to be the same words. Okay, so a line that passes through 2 points like this, called a secant line. A line that passes through 1 point and moves in the same direction as the function, we call a tangent line. All right. So the idea is we're going to use the secant line to approximate the tangent line. So let's see, if I connect these 2 points and I draw that secant line, is this secant line that I've drawn here, is that a very good approximation for the tangent line? And I think we'd say, no, not really. I mean, I guess they're both positive, but no, that line is really nowhere close to what the tangent line is doing, and the slopes are not very close either. You're right. What if, though, I created another line where my x value was closer to a than it was before? Maybe something like this. So I've taken this next x value to be about halfway between. It's not so important that it's halfway. It's just that it became closer, like almost think of this x value as sliding closer to a. So now I've got my x value here and it's got a new point, and now I'm going to draw that new secant line. Hey, you know what? I think we'd still say this new purple line is still not a very good approximation for the tangent line, but we're getting better. Let's do it again. Let's move this x value even closer to a little bit. How about this? Okay, now here's my point. We're still using the same green point there at a. I draw a new secant line. Now we're talking. This new secant line is an even better approximation for the tangent line. Let's do this one more time. I think you get the idea, but let's do it one more time and really, okay, another tangent line. X is getting closer and closer, and now this latest tangent line is an even better approximation. Excuse me, this latest secant line is an even better approximation for our green tangent line. So what is happening here? Every time we make x closer to a, we get a better approximation. Okay, keep that in mind. Let's use the same image kind of as a reference. Again, kind of going back, we really want to know the slope of the tangent line. That's what will be the instantaneous rate of change of our function at that moment. So let's think, let's calculate the slope of our secant line. We can do the slope of the secant line because there are 2 points that the line passes through. We're going to use, our formula for the slope. We learned way back in algebra, m equals y2 minus y1 over x2 minus x1. When we do this, we're going to think of x as being the x2, all right? And we're going to think of a as being the x1, just the way that we're going to go about it. You might think, typically we think the point on the left is x1 and the point on the right is x2 usually. We're going to switch it here, and that's okay because, the parts of the numerator are going to reverse as well. So what would be the slope of our secant line? Here we go. Using our formula, we would end up with m equals f of x minus f of a over x minus a. Again, x is our x2, a is our x1. What would that make y2 and y1? Well, it would simply be those values plugged into the function. Those are the y values, right? So, if we're using, maybe that closest point here, just for an example, then, wherever that point happens, the y value, that's y2, and the y value for a, that's y1. So the x values and their corresponding y values. There you go. The reason why we like to take x as the x2, because we want the f of x to come first and the x to come first and the f of a and the a to come second. Is the only reason why. Okay, so this is interesting. We know the slope of the secant line. How is that helpful to figure out the slope of the tangent line? Well, as we noticed before, as we slide x closer and closer to a, the slope of the secant line gets closer and closer to the slope of the tangent line. All we need to do is take this same formula and add one new element in front of it. And yep, it's a limit. The slope of the tangent line will be m equals the limit as x approaches a for f of x minus f of a over x minus a. Same formula for the slope of the secant line. All we got to do is now say, all right, still perform the same calculation here, f of x minus f of a over x minus a, but now think of x as moving. It's like it's in motion and it's approaching a. Now what's great is, because the way that we've defined a limit, it will never actually reach a, right? If x got to a, it'd be f of a minus f of a over a minus a. We'd have 0 over 0. And that wouldn't work. That's what happens when you try and take the slope at just a single point. The y values are the same, the x values are the same. It doesn't work. You get 0 over 0. But because limits, it doesn't matter what happens when you actually get there. It matters what happens as you are approaching a. We can get an answer for the slope of that tangent line. It's so clever. Oh man. And that's the genius, obviously, behind calculus. And it's, in one sense, it's so simple when you see it, but wow, like who came up with this is incredible. Okay, where's this going? We're going to do some examples here in a second where we look at some actual functions and some values of a, and we're going to figure out the slopes of these tangent lines. First, just before we get to that, need to mention this derivative notation. So whenever we learn a new concept in math, there's always a new notation that goes with it. And that's something, right, we got to get familiar with and comfortable with using. So what we're going to do when we find derivatives, we find the slopes of these tangent lines. We're not going to say that the slope of the tangent line is m any longer. We're going to use a new derivative notation. So it turns out there's a broader application of derivatives than only thinking of it as the slope of a tangent line. That is what it represents graphically, but we don't want to limit it to that, is what I'm trying to say. So instead of writing m, we're going to write this. You read that as f prime of a. It's like a little apostrophe right there. And it's equal to exactly the formula we just saw for the slope of the tangent line. The limit as x approaches a, f of x minus f of a over x minus a. So there you go. Who came up with this notation? I don't know, but it's pretty simple. And, you know, it's about as close as you can get to f of a, right? But it means something different, right? With that little prime that we call it, the apostrophe. Okay, so we'll be using that in a little bit. One last thing to mention here, the meaning of the derivative. So we've used some of this language already. The derivative, we're going to use that word. It turns out we don't want to be saying the slope of the tangent line over and over and over again. Nor do we want to say the instantaneous rate of change. Now, find the instantaneous rate of change, find the slope of the tangent line. We're going to be doing so much of this. We really want to capture that idea with one word. And the word that everybody chose a while back was the word derivative. So when we say derivative, we mean graphically, that means the slope of a tangent line, right? It also means the instantaneous rate of change, or you might even say the instantaneous velocity, which is really similar to a rate of change, but velocity, we're thinking of just always something like moving through space, right? Where a rate of change might not be anything actually physically moving. It might be, you know, I think I use the example like dollars per year or something like that, that doesn't have an actual like physical representation or meaning. So all of these things, you know, if you see problems, say in the homework, and they say, find the slope of the tangent line, you know, they mean find the derivative. Or if they say, find the instantaneous velocity, right? You know, okay, that means I'm going to need to take a derivative. There are some, this isn't a complete list. There are other things that could indicate that you need to take a derivative. There's kind of niche and specific words kind of in context. But these are by far the most prevalent and the ones that we'll use in this class. Okay, we're going to do some examples. These in a moment. I think we're going to stop this video here and then we're going to dive in.